And we are back, and we are going to get into one of the problems that we're going to talk about today, which is the tire blowout 0.7 miles from ATI plant in Louisville, Ohio. So when I was working in industry, part of the job was to essentially, I was in Pittsburgh, and I would drive to one of our production plants in Louisville, Ohio, to work on essentially basically improving process development and running a couple of experiments. And a lot of times those experimental runs would be at 3 a.m. in the morning. So I was driving in the cold in January, tire blew out, 0.7 miles, I'll never forget it, from the plant. And so I had to take my newly minted kind of emergency kit rope pack and pull the car 0.7 miles into the parking lot. Why didn't I just drive? I always remember my dad saying, if you have a flat tire, you're going to damage the rim. Little did I know, if you pull it, you're still damaging as well. But anyways, this presents a nice opportunity for us to look at this problem and to analyze it, essentially looking at statics. So I think that the Jeep has a mass of approximately 1,600 kilograms. The coefficient of friction between the tire and the substrate is approximately 0.3. I can exert a force of 3,000 newtons. Will the car move? Now, in order to analyze this problem, we are going to implement our statics problem-solving algorithm. So first, we need to idealize the real system. So let's look at it, let's make some reasonable assumptions, and let's idealize the system. Then we're going to define our coordinate system, free the body, again, remove, essentially focus only on the body, draw our corresponding, external forces that act on the body, and remove all basically surfaces. Then we're going to write for our equilibrium expressions. What are our equilibrium expressions? Some of the forces must be equal to 0, some of the moments must be equal to 0, and we're going to solve for our unknowns. So let's idealize this problem. So first I'm going to assume that these tires, the front tires here, are able to, basically are free to move. These are locked. So that's essentially the system that we're working with here. So if that is the case, how are we going to approach this problem? Well, let's go into it. So this is kind of our idealized system. So we're pulling the rope. So there's going to be some force acting on this here. So I'm just going to call this some force 1. Acting on our system, it's at an incline, and we're given essentially the dimensions that we're working with here. So let's draw. So this is our idealized system. And there is also the weight is essentially acting at this point here in the centroid. We've already done and calculated this the centroid for you, so you don't have to worry about that. So with all this information and this idealized system, so we are considering friction, let's go ahead and draw the free body diagram and see what we can be working with here. So I know that there will be a reaction force on these tires as such. I also know where is the impending motion. So if this tire is free to rotate, I don't have to worry about friction, and I'm going to neglect rolling resistance of the tires. So I don't have to worry about friction here, but the impending motion is going to go this way. The contact surface is right here. So I need to be, for friction, what do I need to do? I need to be tangent to the contact surface, and I need to be opposite the direction of impending motion. So if I look at my free body diagram here, we can express that just as we see here. So just like this. So react normal, normal, we have our weight. Our weight is just going to be the mass times gravity. So we had the mass of the Jeep. The force, again, I claim that I can exert a force of around 3,000 newtons. And we have our coefficient of friction. We have our free body diagram. This looks to be all correct. We have our coordinate system we've already defined previously. What do we have to do now? Well, let's write out our expressions. And what I'm going to do is I'm going to write these out simultaneously in Mathematica, and so we can eventually solve for this. Because we want to set up, and one of the focuses we're going to do today is set up the expressions, define all the variables that we know, and then set up a system of equations to solve for our unknown. So let's let our programming skills and Mathematica do some of the heavy lifting for us, because that's what we want to do as engineers. So we want to just we want to solve the problem, and we want to look at the system we're dealing with. All right. So if Mathematica ever decides to open, there we go. All right. So let's go ahead and define what we know in our system. So I know that the mass is equal to 1,600 kilograms. We need to be in SI units. Gravity, 9.8 meters squared per second. Good. Theta is going to be 25. What else do we know? We know that our weight is going to be m times g. We also know that our coefficient of friction, we'll just call it mu at the moment, is going to be, well, actually it's our static friction, or maximum static friction, will be this, and we can set those up. Now, first equilibrium expression. Sum of the forces in the x direction must be equal to what? So that also has to be equal to 0. Just to kind of set up, what is this distance here in terms of if we know f as a magnitude? Well, it's going to be f times cosine of theta. This will be f sine of theta. So we'll just keep that in mind as we continue to work through this problem. So I'm going to do my sum of my forces. So force in the x direction, that equation must sum to be equal to 0. Set it up equal to, what are my, and actually I can define this here. My f sub 1 is going to be equal to, again, that's my friction direction, so it's mu s times fc. And I want to hide that. So in the x direction, I simply have f sub 1, positive direction, good, minus f times cosine of theta, and I need to be in degree mode if I'm going to be working with degrees. Excellent. How about f sub y? Set equal to 0. And in the y direction, I'm going to have fb plus fc plus f times sine of theta degree mode. There we go. So, what are our unknowns in this problem? I don't know fb, I don't know fc, and I don't know f. Everything else I know in this expression. So, if I have 3 unknowns, how many equations do I need? 3. So I need to look about a moment. So I want to pick and actually calculate the moment right here. So this is our moment about c. So I'm going to have to go up here and say m sub c equals 0, set equal, and now let's go ahead and solve. So if that's our moment, and what's our lever arm? Remember, moment equals df. What's our moment arm for fc and f1? 0, because we're right there. So we can look at the line of action here for our weight. What is the perpendicular distance to that arm? Well, let's look up in the diagram above. It'd be useful if I have it here. So that's 4 feet. Be careful now. We're in SI units. So I need to convert that 4 feet times 12 inches times 0.0254. Well, that will convert from inches to meters. So I'm going to go ahead and do that. But actually, we'll do the lever arm right now. So 4 feet times 12 times 0.0254. So that is my perpendicular distance, the line of action, the perpendicular distance. And if I were to do my right-hand rule, how will this rotate? Counterclockwise, so that is indeed positive, so I can put this times my weight. Fantastic. Great. So, what else? Let's do B. So, my line of action on B, so my line of action is like this. Perpendicular distance to the origin is here. So again, we can look that up. So that's going to be 5 plus 4. So let's go ahead and let's do for the moment plus. So 9 times 12 times 0.0254. And let's see if that's indeed a plus. So if I were to do our right-hand rule, can I curl around and reset direction? No, it's actually in the opposite direction. And we can kind of see it too. It's going to go clockwise. So I'm going to set that as a negative time FB times that. Are we done? Finished? Not quite, right? So let's go ahead and let's look at we have this to consider as well. So let's first look at our cosine component, our x component. So this is my line of action that goes through here. So my distance, the perpendicular distance, is going to be that distance above, which we were given to be 1 foot. So if I look at that, and is this going to be a positive direction? Yep, I could curl around. So I can go ahead and say that's going to be a plus f times cosine of theta times degree. And then the distance is going to be simply, actually, where's that distance? 1 foot times 12 inches times 0.0254. Fantastic. And finally, again, my line of action, the perpendicular distance to that origin, and if I look at the direction, it'll be negative, but let's calculate that distance, which will be 9 plus 1.6, so minus f times sine of theta times degree, which is going to be 10.6 times 12 times 0.0254, and that should be it. So we've got it. 3 equations, 3 unknown. I can just set fx, fy, mc. We got it. That is, oh, excuse me, I think there is one little, I think I see the error here. Again, you want to go slowly through this. So one of the things we missed, FB, FC, we did not subtract weight. Ooh, always be cautious and be careful about that. So we've got this here, we got this here. Now we can solve, and we've got it. That's it. So we can see now that, will I be able to move this? Yes, actually I should be able to. If I can exert a 3,000 force, I should be able to move that, because the maximum would just be this required to basically reach or achieve static equilibrium. So be careful, be cautious, make sure that you don't neglect all of your expressions. But we've got it. That is it. So now we are absolutely ready to go, and we can go ahead and move forward with our next problem. And our next problem will be, actually, when I exerted my 3,000 newtons of force, I wasn't able